So let me end this chapter with one more application of the uniform distribution. We spoke earlier about how it can be valuable by way of the inverse distribution function. If I can generate uniformly distributed R's, in fact, by using an inverse distribution, I can get a random distribution of variables from any distribution f I want. But I also want to point out that there are many applications in finance, and particularly to actuaries, in which you can use the random variables R directly to a finance application. So let me give you a couple of examples. The first one is generating binomial paths. We know in our binomial lattice that the probability of an up return is p star, and the probability of a down return is 1 minus p star. So we can easily generate a path of ups and downs with a simple algorithm. We generate an R, and if R is less than or equal to p star, we get an up step. If R is bigger than p star, then we get a down step. So in a binomial lattice, the random variable R is uniform, 0, 1, that a uniformly distributed random variable directly gives you binomial paths of stock prices by simply identifying at each step whether you use a U or a D to get to the next step. And it's just if we're generating a path using the log normal distribution, then we have to take each R value, generate a random normal, and then the normal gives us the return and the price. If we're doing it with a binomial, this uniform variable R directly tells us whether we go up or down. Simple. Other applications that you would have would be, for example, in let's say that P was the annual probability of a default on a bond. And I want a model where I go through time with this bond and it pays me until it defaults. Again, I can do the same thing. I generate a random R for each year in my model. And if R is less than or equal to P, it defaults. If R is greater than P, it stays in good status. And this does exactly the right thing, because the probability of default in any year is P. And actuaries have long used the same kind of a procedure for many of the decrements of mortality and morbidity, where I might use a QX as the probability of death. And of course, it's a function of age. But I can generate an R in any given year. And if that R is less than or equal to QX, then I'll model in my portfolio a death. And if the R is bigger than QX, then I have a survival. And it works equally well, and naturally we would change the QX each year in our mortality model. And it works equally well in determining in a large group of individuals stochastically generated claim models. So this is a very powerful and applicable procedure, and I didn't want to end this chapter without highlighting that the uniform distribution is a very powerful tool in any kind of a binomial model, whether it's a sequential binomial model, for example, in generating paths of stock prices, could be a sequential survival model, generating deaths in a survival model, or even a sequential default model, where we're generating the, how many bonds default in any given period of time.